My name is Shane Robertson.
I'm Tyler Kim.
Jasmine Zhao.
And I'm Sydney Ferguson.
And this is our analysis and review of Chicago energy usage. For our project, we wanted to find correlations in energy usage and other factors. We plan to do this through graphing, data analysis, and general observation. We wanted to better understand what we had. So we went through and mutated the data, we just worked with our data best we could. Our general methodology was going through comparing data to itself to see if there was any repeated variables. And then we got a general census of what that was. We also went to things like Google or Google Maps to see what was what. So like with community areas, which we'll see later, we had to figure out what those areas were so we could better understand why they were the way they were. Our results we'll go into later. Up next, research abstract proposal.
Yeah, so we had 4 primary questions going in to this research. The first one is, are there certain communities that utilize energy more than others? This is just to show general trends across different neighborhoods and different areas of Chicago. Next up, we have certain building types more likely to use more. This can help give us some insight into demographic dynamics involving energy usage. And, again, it also ties into the first question of which communities are using more energy than others. The next question we have is higher population should use more energy. Does the data show this trend? This question is more so to kind of make sure that we're examining that data properly. Because, if it doesn't show this trend, it means that we've failed at observing the research and the data how we're supposed to. So this is just to make sure that things are consistent in our research. And then the last question we have here, in which months do we see the highest energy bills? Again, this is important just to examine trends going on throughout the year, just to kind of tackle some assumptions we have, such as maybe certain houses use more energy in the winter than in the summer. Just some important variables to keep in mind. Once again, we have the name of the community that the building is in, the type of building, and whether or not the building uses electricity or gas.
Yeah, and the next part is data dictionary. So as you can see at the top of this page, you can find the link to the original dictionaries that we find. And this kind of variable that we named for the code that we use in letters, I'm going to represent what that means. So first of all, you can see the common area names. This is the name of communities that the properties is buying. And the census block is just represents the census block at the property falls within, just looks like its names. And for building types, there are totally 3 values inside, commercial, residential, and industrial. So commercial buildings usually often stores and for-profit properties. Sometimes it's apartments, and the residential is usually family house, also could be apartments sometimes. And industrial buildings, just like factories and production lines like that. And building subtype is just the splits for the subcategories for the building types. And next is total populations and total units. So total population is just how many people like living the properties, and units is just how many living units in the properties. And the next several variables like average stories and average building age. So basically it's like average number of stories on properties and average age of buildings on a property. And also the next one is average house size. Just looks like their names, the average number of family members living in each properties. The next one is occupied units. Is just some variable that means the number of the living units that are occupied on the properties. The next two is kilowatt hours and the thermals. That is just it's like electronics usage and gas usage, like by monthly they use for the properties. And we also like calculate the kilowatt hours totally, and also the mean, max, minimize the number for kilowatt hours and thermals that just like represent different electricity usage and gas usage for the properties. And we also get the square footage for the property that hooked up with electrical and gas usage, and it named divided by kilowatt total square footage and thermal total square footage. And we also get the thermal total monthly gas usage, this kind of variables. And the last two is the number of open electric accounts and open gas accounts on the properties, and we name them electric accounts and gas accounts.
Okay, next we go on to the data exploration summary. And in this, we are going to answer the questions that we mentioned earlier. The first one is, are there certain communities that utilize more energy than others? Based on the graph, the loop is a massive outlier, which needs to be removed to see better data, as you can see. And then after removing it, the graph shows that the areas near west side, south side, and north side have a heavy variance compared to the rest of the data. So to get a better picture, we need to divide it by building type, which leads into our next question, which is, are certain building types more likely to use more energy? From this graph, it's obvious that industrial is a major outlier, most likely caused by the loop area that caused the previous outlier. All this graph really shows is that industrial uses a massive amount more energy than residential, which is pretty logical. The next question is, higher populations should use more energy. Does the data show this trend? So as we look at the graphs, currently the non-categorized buildings are showing a somewhat position correlation coefficient. However, this is altering the data that we see for commercial, industrial, and residential buildings. It should be noted that this shows us that we need to consider using the non-categorized buildings if we want to get good data points. And it shows that this data needs a lot of cleaning. So below, we repeat the same graph, but we remove those uncategorized buildings. And from this graph, there does not appear to be a pattern in energy usage. So the assumption we made is wrong, or we're missing something, and this is something that we can look into further. And then the next question is, in which months do we see the highest energy bills? This graph shows the trend of higher electric bills in the summer and winter. However, given Chicago's colder climate, you might assume their energy usage should be higher. The above graph, the one shown now, does not factor in gas usage. So below, we recreated the graph using natural gas instead of kilowatts. And you can see that there is a shift to gas as it gets colder, which accounts for the lower than expected energy use from the prior graph.
All right, and then next up is our data cleaning process, which we followed up with the we did to follow up the data exploration summary. So first of all, we factored the columns. So we needed to factor the community area name, the census block, the building type, building subtype, gas accounts, and electric accounts. There were some columns that we wanted to drop, and there was incomplete data in this that we wanted to remove. So we had to get rid of them. We did that using this. We calculated the total to compare to see if it was, here we calculated the kilowatt total for each unit to see if the kilowatt hour total was redundant, and we proved it was, but we kept it anyways to help us with analysis. Removing columns that had a significant amount of null data. So this function goes through and it summarizes all of our data on the column community area name and all these other variables. This counts the number of null instances for each column we have. We can see some of them are quite empty. So clearly we have a lot of data to go through and shuffle and reconfigure. So the first thing we did was we removed all the rows that had a null census block column. This helps clean up a lot of the data. Along with that, we just went ahead and dropped some columns that we didn't need because there was a lot of null values for them, and we just didn't need things like standard deviation because we could calculate that ourselves. Then we went ahead and removed a lot of the variables. We went through and checked to see what was null and what wasn't. With this, we can see that if we filter out everything that doesn't have the kilowatt total hours, we end up with a very consistent data set. All of these numbers represent the number of instances which are not null, and since they're all the same, that means our data is clean and that we have a full set of data. Now that we have a full set, which is 57,000 different rows to work with, we are more than ready to start looking at the data. So we go back to what we did before, which is look at the energy usage by community. And we can still see that there are heavy outliers. We have the loop, we have near west side, near south side, and near north side. Instead of removing these communities, we instead removed the outliers that were within the entire data set. So we removed the top 4%, leaving the 96th percentile. This smoothed out our data significantly, as you can see here. And we kept what we had here, just it would help us to predict better and get a better understanding of the most relevant data. And then we went ahead and checked gas usage by community just to see if there was any outliers in it, and there are few, but we didn't have to do a whole lot. We only removed the top 1%, and just doing that gave us a much smoother graph. All right, next up, we converted each month into a different column, so into a different row. So instead of having all of the data for the entire year of 2010 on one row, we split it into 10 different rows for each row, which gave us a lot more data to work with, and additionally gave us a lot of it allows us to analyze the data from a different perspective. So scroll down. Yeah, so we just expanded the data. With that, then we just wanted to check to see how good our data is now. So we used a more obvious correlation to see if there's any outliers, anything excessive. We used kilowatt hours square footage and kilowatt hours total, which should have a positive correlation. And we saw in the data, for the most part, this is true, and it's true enough that we felt we could move on. Now for the analysis and explanation part of it. So we still have a link in all the pages that links to our markdown files if you want to run them yourself. The analysis and explanation. So our first question was, are there communities that utilize more energy than others? So first, we went ahead and graphed the thermal usage, the gas usage, and also the electric usage. as can be seen here. And it is clear that there are definitely communities that use more, as we proved earlier. And so to analyze that, we went ahead and sorted it by the usage and filled it with the population range. So as you can see, from the bottom up, darker colors were lower population, brighter colors were a higher population. And we can see there is certainly a correlation with higher energy usage and a higher general population. This set includes things like commercial buildings and residential buildings. So we can likely assume that the north side and south side are probably more commercial than the rest. Yeah. Next up, we repeat the same thing, but with units, just to get a better idea of what this whole graph was. And we got very, very similar results. Yeah. So to get a better understanding of the data, we also wanted to see if there was a more common building type with higher energy usage communities. And so what this chart does is it gets the most common building type and displays it as a color. So the most common building type for each community, blue would mean single family, green would mean residential multifamily, and red is commercial, but we only have one commercial. As you look at this data, you can see that it slowly goes up. As the energy usage goes up, so does the number of multi-resident house buildings. So we assume that the higher energy usage areas have more apartments. All right, question, are there certain building types that are more likely to use more? As we saw before, there were, but after cleaning our data, we want to reanalyze this and see with the building type and subtype merged. So we can see the industrial buildings have a very strong high just value that sort of we feel can mess with our data in an analysis. We can also see commercial was next up, and municipal, multi. We decided in the end that we really only wanted to work with the residential or living spaces because that was something that we could more properly analyze, because commercial buildings that run things like stores or tourist traps are a lot more difficult to analyze and are sort of considered outliers than compared to the rest of the data set. So next we decide to remove certain building types. But before this, we want to see, should higher populations should use more energy? Does this data show this trend? And as we found before, it really doesn't, and we don't know why. So here we're going to go ahead and try to figure out if it's just a matter of the variable we're using, because there's also kilowatt mean, there's kilowatt max, there's kilowatt min, and then kilowatt total. We found that kilowatt max and kilowatt total were our best variables, but we went ahead with kilowatt total because it gave us the most data. So the outliers made it difficult to tell if this was an effective method, and we removed the outliers by filtering the excessive total kilowatt usages that were greater than 1 million, as can be seen here. And then we also tried to see if the kilowatt square footage was messing with our data. And from this, we can see that there were 2 different factors that were influencing this. So because of the triangular shapes of our population and kilowatt hour function, we found a result of the square footage usage. And so we took this into account and just decided to look at different variables to see what we could best find correlations for. So instead, we checked to see if we could get it from the kilowatt square footage and kilowatt total and see if there's a better correlation. We switched total population and square footage, and we saw a much stronger correlation with square footage and totals. All right, and moving down, we took the kilowatt square foot mean and wanted to see if it would show us a better correlation. It didn't, so we moved on to the next set and we switched to the random forest model because we weren't getting very far with the other results. So to do this, we simplified the data. We had to remove certain things like community area name because there were too many factors for the treated process. We also then standardized the data by using kilowatt hour per account, which divided the kilowatt hour total by the total electric accounts and the therm usage total by the number of gas accounts. And then we went ahead and removed the more statistical based data, like the mean, max, min of the different energy usage types. And then we go ahead and plot it just to see. And we have a very high correlation between therm per account and kilowatt hour usage. This showed us that this had a stronger influence than we thought. And so we wanted to see more information about this. But beside that, we also saw that building type was important, which we sort of predicted prior to this. Square footage seemed to have a strong correlation, as well as therm square footage, though we also know that the therm square footage was almost always the same value as kilowatt hour square footage, so it wasn't surprising. We also saw building age was rather important, and the rest of the variables sort of dropped down from there. So then we just to get an idea of what caused the change in the why the therm was more important than anything else. We graphed the therm usage and the kilowatt usage, and we can see that there is a very clear correlation. The energy usage gets higher, the thermal usage gets lower, and vice versa. So this shows us that our data could use more exploration, but we also know that most of our influence of the data was from therm usage. All right,